Okay, there's a few last minute things we need to do about implication to really wrap it up. And it has to do with the very subtle notions of true and false, and whether that's the only things we allow in our logic. We've seen classical logic distills everything into true and false and lets you have a story of implication, which is just to write down all the ways that P and Q could be true or false and have a list of what you call the implications. As we moved around, we saw that applications can vary. And one of the applications we want to leave on the table is the reality of coordinating data sets. Data sets are often so quick to move. In a database, transactions happen right away, and they may never be present again because new transactions update things. So it's hard to say that something is wrong. It's just so ephemeral that it can't be tested as twice. So we have to learn to live with a logic where something is true because it was true when created, but it may not be true the next time. And we shouldn't throw everything out simply because we found a contradiction of some sort. We're trying to think of that as a localized contradiction, which doesn't spread to spoil everything we're working on. That's the role of, say, a paraconsistent logic. Now, it takes us way too far to study paraconsistent in general. I just want to give you the flavor and the details of how the sequent calculus lets us do this. Fundamentally, I want you to look at this rule here and think about what it's saying. We're saying that P together with not P entails falsity. This is based on a few assumptions that we might be making. What we could be saying is that not P is simply a shorthand notation for an implication. This is just saying I want to replace it with equivalent symbols. I could be saying that P implies falsity. If I take it like this, then rewriting this is equivalent to modus ponens. Let's see how. The not P becomes P implies false. And the P part stacks up below. The conclusion is simply modus ponens. If P implies false and we have P, we get the conclusion, false. So this is already packed in to our modus ponens rules. If we have implication as part of our rules of logic, which is there in almost every logic, and if we take negation to be this, we're guaranteed to have a notion of P and non-P giving us false. So why is this then even something we can talk about as paraconsistent logic? We seem to want situations where P and not P can coexist. Something can be both true and false and still leads to falsity. The key was, what do we want false to do? In a non-paraconsistent logic, such as a classical or intuitionistic logic, we add a rule called explosion. Explosion says that we can take any proposition at all, and it follows from falsity. That explosion rule is based on having a two-setted type true and false. We're not allowing some murky middle ground. And that's what we have to reject in paraconsistent logic. In paraconsistent logic, we simply don't add this to our language. It's not one of the resources we have in our context. And therefore, this implication, which has to be there, doesn't lead to a disaster. It doesn't lead to disproving everything. It lets us still have a lid on the insanity that is being true and false. Now, to get this all patched up quite right, you have to technically, you move to what's known as a multi-mode logic or a three-term logic at minimum. You might need to recall how we wrote down true and false at the beginning. Let's put that on the board. Okay, so I've got them up here. Remember that we always settle for a language. In this case, the language is not going to be important until we get to how we add our paraconsistent thing. So we'll have true and false, true and falsity, and these will be our Boolean expressions. In an intuitionistic logic, we stick with the sequent calculus to describe the process by which we get the true and false values. So for example, context always entails true. True is true. False is allowed to lead to anything. That's the law of the explosion. We're going to want to do away with that. We get implication rules by simply saying if the context together with the premise entails Q, then we can package that up in the notation P implies Q. It's an operator. It's simply packaging what we see in the premise into the bottom. We can also then use what we've packaged later on if we discover our context has a P, and we knew by having packaged some previous time that P implies Q, we get to get Q out. So it's simply setting up our situation. Now, that's a very process-oriented implication. We saw that there was another way to think about implication, and that was simply classically. Classically says, if I forget about why premises are true and why conclusions are true, I just want to know when they're true, then I just need to have a table of the true and false values. So I put in a column for P's that could be true, true, false, false, and Q could be true, false, or true, false. That's all the combinations of P and Q. Then I simply write down in my table what actually happens when these things occur. So I'll notice that when both of them are true, I get a true implication. And when both of them are false, I get a true implication. This is saying that false implies false. When I have false, I'm allowing it to entail true. Again, this is that secret of hiding it inside of the premise being the context. The context can still lead to Q even if P isn't true. So false can imply true. The only one we don't allow, we disavow, having the premise be true and the conclusion false. If we put it into this system, neither the context nor the premise led to Q because Q is not true. Therefore, we wouldn't get this. That would be illegal and it wouldn't have happened in either intuitionistic or classical logic. Now, there is a way to do the paraconsistent logic in both of these. However, I'm going to focus on the simplest version. I'm going to try to take this classical true-false thing, and I'm going to try to sneak in a new symbol, a symbol that lets us talk about another state, a state which will eventually be the true and false. So I'm going to stick a further term here and call it M. M for maybe true and false. We'll have to figure out what it is. And then what I'll do is I'll create a new table with true, false, and M, and we'll see what rules we want for the implications in that case. That'll be one way to introduce the type of paraconsistent logics that exist. Now, the one I'm going to give you is just one example. It's called the logic of paradox. There are many ways to make a paraconsistent logic, just like we saw there are many ways to make implication. We can count the number of premises and combine them in different ways and make a nuanced version. All of these had further rules like weakening and contraction. So I'm simply racing to the finish line and getting the true false version of paraconsistent so you have one to play with. If you really need this in your research, take a specific course on the topic. Okay, so we're set up to do our three-valued truth table now. The third value is the maybe. We don't know what this means yet. And it turns out you can use three-valued logics to study many kinds of logics beyond paraconsistent, but we'll stick to our goal here. So let's think what has to happen. There are several goals we could ask for implication. One could be that we want to preserve truth at all cost. Another thing is that we want to avoid paradoxes or some kind of loopholes where false is leading to things that it shouldn't. Sorry, where true is leading to things that are false. The ways we think about this lead to some of the choices. I'm going to pick one. What I'm going to say is that we shouldn't surprise ourselves. If we have something false, it should be able to do whatever it was doing before. That's how we've seen it work before. False could lead to true or false. So there, I'm going to copy down the rules exactly the same way. This could happen, this could happen, this could happen. I'm allowed to have false lead to true. I'm allowed to have false lead to false. So it makes sense that it could lead to true and false. Both of those, all three of those will now be true. What about up here in the true column? If I have true together with true, what do I think I want my implication to do? Well, in all other implications, true has led to true. So we better not mess with that. That would seem like a strange place to start making a new stance. Okay? Now let's think about true implying false. That's certainly one we wanted to avoid in all our scenarios, because then what does implication mean? We want logical reasoning that if something is valid, it leads to more valid things. So let's disavow that one. Okay? Similarly, let's now come back to these. What if M stands for true and false? What should we do in that situation? Well, one thing to do is to say, well, at least it's somewhat true. Since it's both true and false, true is in that storyline. So therefore, true and true should still be true. What should we do if it's in this middle state, M and N? We could treat that as a situation in which we don't have enough information. We could also say, well, since M is true, we could think that that's true. And since this is true, that's kind of true, but it's also false implying true. And then it gets tricky. Let's put an M right here. Because that way the answer is sort of tricky. It's a bit of true and a bit of false. The implication isn't clearly true and it's not clearly false either. There's a way in which you can mix and match. And what about something leading to false? Here we have a clear definition. Since M can be true and false, there's at least one scenario in which true would lead to false, and we don't want that. So we'll disavow that one. We simply don't let that one get off the ground. Let's come back up to here. What about true implying M? True implying M has a difficulty, at least in one scenario. True could imply false, since this is both true and false. So that would have to be false. But true could also imply true, since this is both true and false. So that would have to be true. So the conclusion here is a mix. Maybe it's true, maybe it's false. So we'll put an M here too. You now see that we've created a table, and we could just use this as a reference chart. Even if we don't reason through it every time, we just accept that as fact, we could arrange that true and false behave like this. You can now see how to go write a computer program. You have a computer program which reads if, and it takes the premise in. And what it's going to do is simply switch values based on the choices. If it sees true, it'll follow the rules that are here as to whether it continues. If it sees a false, it'll follow the rules here to continue. And if it sees a mix of true and false, it follows these rules. It gives us a clear way to precisely compute in paraconsistent logic. We can start to make programs that reason the way we're trying to think. And it might be that when you reach M to M, that you should go back and recheck your database for new additions and re-update it. Or you might decide that at this point, you tell the user, what would you like me to do in this situation? Please pick for me. But the key thing is we don't have to crash the program. We don't have to program something illogical. We are simply switching between more cases because the subtleties have emerged. I want you to think about this as one of many huge opening world of different logics that are all tuned to study different types of story problems. Your job is to know that when you have a story problem, you have a duty to go learn the logics that could apply for it. They're not always unique. There might be several logics, but don't be stuck on classical logic as the only tool in your toolbox. It'll just make you weaker at solving problems. Now, as we go forward, we want to start to lift this up into new types of thinking. In particular, it'd be great if we could write programs for all the math. So we're going to try to wrap up everything in types. As we move towards types, we'll also encounter the mathematician's favorite, sets. Until next time.